Hello, everyone. My name is Nahuel Miron Granese, and today we will talk about the impact of self-interacting dark radiation on primordial V modes. Let me thank the organizers for this opportunity. And I'm working at the University of La Plata and the University of Buenos Aires in Argentina, and I'm a postdoc founded by CONICET. So let me start with an observation that in terms of the work of Michael Turner, the past 50 years has seen cosmology go from a field known for the error being in the exponents to precision science. So in 20 years or so, we pass from this to this, and for example, from this to this observationally. So the precision cosmology era has two parts. On one side, we have the increasingly accurate knowledge of the cosmological observable, and on the other side, we have the development of models at the dominant, but also the subdominant or perturbative level. Because in order to reach the precision of the observations, we need to develop both dominant and also the perturbative phenomena. So in this way, we are working on a major project in which we try to describe non-ideal and non-equilibrium properties of matter, mainly during the early universe, and find the imprints of this phenomena in the cosmological larger scale fields we observe today. For example, in the primordial gravitational waves, in the primordial magnetic fields, and particularly in this case, in the cosmic microwave background, in a word that will appear soon in the archive. This is a joint project with Claudia Scoccola, Esteban Calceta, and Alejandra Candus. So coming back to the impact of self-interacting dark radiation, the first ideas and questions that we had at the beginning of this project were, we know that every model of inflation produces gravitational waves. So, and we also know that there is an interplay between the primordial gravitational waves, the primordial plasma, particularly the ultra-relativistic species, and the CMB modes of the CMB. So we know that the polarization observations that we could observe today are affected by this interplay. So our question was, usually the ultra-relativistic species are free streaming. So what happens if we introduce interactions, and let's say that we want to study interacting ultra-relativistic species, primordial gravitational waves, and CMB modes interplay? Is there a change in the primordial gravitational waves that we observe today? And is there a change in the CLs of the B modes, and particularly if there is a change in the estimation of the tensor-to-scalar ratio, if we consider this interacting ultra-relativistic species. So, well, to start, we know that inflation produces primordial gravitational waves, and if we add the Thomson scattering during recombination, we know that there is a specific pattern in the polarization called the primordial B modes. Of course, the gravitational waves, the evolution is determined by the traceless and transverse projection of the spatial part of the Einstein equation. And it is interesting that the right-hand side of this equation is related to matter or energy due to the anisotropic stress. So for an ideal fluid, this anisotropic stress is vanishing, but nonetheless, for weakly interacting or decoupled ultra-relativistic species, we have non-vanishing anisotropic stress. So it affects the gravitational waves, and then this whole interplay affects the primordial B modes. So in this case, we will consider ultra-relativistic species in the primordial plasma in the following way. We will have thermally produced ultra-relativistic species. For example, as neutrinos, we're considering non-photonic radiation, of course. Neutrinos and dark radiation. For neutrinos, we have the well-known abundance of neutrinos, and the interactions will be summarized in this gamma nu. And for the dark radiation, we will have this delta N effective, which is basically all the non-photonic radiation minus neutrinos. And the interactions in this sector is determined by this gamma dr. So usually we have these bounds for neutrinos and dark radiation, and they are completely decoupled. So we want to study the effects on the spectra of primordial gravitational waves and the CMB polarization B modes due to interactions within the sector. And schematically, we have, if we introduce non-vanishing interactions for the DR sector, will we have a variation on the gravitational wave spectrum? Will we have a variation on the primordial primordial B modes of polarization? And finally, will we have a variation in the estimation of the tensor-to-scalar ratio? These are the questions that we had. Well, what kind of simple interactions are we able to introduce? There are a lot of types of interactions that we can see in this plot, but in this case, as an example, we will focus on a self-interacting and axion-like particle with potential like lambda 5 to the 4, in which the interaction rate scales as 1 over a, and it is possible to define a constant co-moving polarization time as this. So what are the constraints for this dark radiation species? Well, the main constraint is on its abundance. Delta N effective should be lower than 0.4, being very conservative, but the parameter of the interaction, which determines the strength of the interaction, in this case, lambda 5, is poorly constrained, as we can see in this plot. These arrows indicate Waking transitions and peaky features, but the coupling constant is basically unconstrained. So here we see the relation between the interaction rate, the coupling constant, and the relaxation time. So we can, of course, parameterize the gamma, the interaction rate in this way or this, and here we have the equivalence, and different values of the coupling constant gives different values for set in the redshift at which the interaction rate and the Hubble rate are equal. So this means that if we have higher values for lambda 5, we will obtain higher values of set in, and of course, the interaction will be efficient for a longer period of time. Since this interaction is efficient for later times, it's called recoupling. So since, of course, the lambda 5 is poorly constrained, we can take all these different histories of the interaction rate and do the analysis for the primordial gravitational waves, B modes, and so on. How do we introduce these self-interactions in the DR dynamics? Well, we will do it through the Boltzmann equation, and particularly with the Legendre expansion for the tensor modes and the relaxation time approximation for the collision integral, which defines the interactions. Here we see the terms related to the interaction in the Boltzmann hierarchy. And of course, we should include all these equations within the Einstein-Boltzmann scheme for all the coupled cosmological perturbations. Well, let's go to the results and the impact of these interactions in the primordial gravitational wave. Here we can see the spectrum of the primordial gravitational waves today with and without interactions. And there is a scale determined by the relaxation time that for scales that enters the horizon after the interaction becomes efficient, we will observe no damping due to the isotropization of the gravitational wave source caused by these interactions. But for scales entering the horizon before the interaction becomes efficient, we will observe the usual damping, and we can measure this relative difference of about 10 to 1%, depending on the value of delta and effective from 0.5 to 0.1. We see these differences. So what is the impact on primordial B modes? Well, to analyze this, we need to include the whole equations that we showed before in a Boltzmann solver called a class, and then compute the angular spectrum of primordial B modes. And we observe here, this is just an example with delta n effective equals 0.5, but just as an example, for a wide range of tau. And we know that increasing tau is making basically the interaction efficient for later times, and particularly after recombination, we will see no effect on the primordial B modes. To quantify this effect, as I said, we plot the relative difference in this angular spectrum, and well, we obtain, for the cases in which we see an appreciable difference, this is from 5 to 1%, depending again on the value of delta n effective. And we recover the usual spectrum in the case in which tau is tends to infinity due to what I said, the interaction becomes efficient after recombination, so no effect. We will see no effect here. Okay, the final question is, how can we analyze the impact on the estimation of the tensor-to-scalar ratio? We do not have observations, of course, for the primordial B modes, but we can simulate observational data with some input model and noise, instrumental plus cosmic variance, and a fitting model with the parameter that we want to know. After a Markov chain Monte Carlo procedure, the usual one, we can obtain one best fit parameter, in this case, R estimated, per noise realization. With 500 realization of the noise, we estimate the distribution of the relative bias. Here, R true is the actual value of R in the input model, and we will have 3 types of simulations / analysis, 2 consistency checks in which the input model and the fitting model are the same, with no interactions or with interactions. Here, we do not expect any bias, and the case of interest in which the input model, the real universe, has interactions, but we are trying to estimate R with a model, a fitting model, in which there are no interactions for the dark radiation sector. And here we expect a bias. So the results of the distribution, the evolution of the distribution is here. We have we have the 3 simulations per each value of R, and then as we expect, there is no bias for the consistency checks, but the case of interest, we do obtain a bias. So this bias will be significant if it is higher than the variance of these distributions. So we can quantify this effect by just computing the bias and compare with different levels of noise. In this case, we are plotting here the relative, this is just the bias for different values of delta and effective, with 2 levels of noise basically related to these parameters. But again, what we observe is that the value of the bias is higher or of the same order that the variance, the noise variance. So the main conclusion of this work is that the bias produced in the estimation of R due to the systematic related to the self-interacting dark radiation might be relevant in the data analysis given the sensitivity of the upcoming experiments. Finally, we can study the variation of the result with respect to the coupling constant. And we see that there is a kind of a step-like feature. And for coupling constants lower than 10 to the minus 12, we see an observable bias. But for higher self-coupling constants, higher than 10 to the minus 10, the effect saturate the effect. So, and in between, we obtain slight variations, but of course, again, the main conclusion here is that this effect depends not only on the abundance of dark radiation, but also on the strength of the self-coupling interactions. So here we have the final comments. So you can stop the video and read them. I will only say that the introduction of dark radiation, interacting dark radiation, does affect the primordial gravitational waves, the primordial B modes, and the estimation of the tensor-to-scalar ratio. Let me just finish with an open questions that we might discuss at the conference. And they are, could it be possible to constrain interactions in case of a positive detection of the CNB primordial B modes? Can this analysis be applied to massive particles, particularly to the whole dark radiation, to the whole dark sector in cosmology? And given the complexity of these interactions in the cosmological constant, can we develop a simple effective models that captures the essential physics in order to apply them to reheating or phase transition, other epochs? And finally, can we include those effective models in the lattice codes used in cosmology? So, well, thanks for watching and see you at the conference.